we have two problems, 15A and 15B. 15A should be very, it is not that long, but we need to spend a little bit time on 15B. So let's start working on that. Can anyone read 15A? And I will write down the given values and what values we need to find.
Water flows along a rectangular channel having a width of 0.75 meters. The velocity is 2 meters per second. Determine the volumetric condition.
Thank you very much. So they are saying there is a rectangular channel. That means if I want to draw a 3D of this channel, that is the channel, right? A rectangular. And the width of this one is 0.75 meter and the height is 0.5 meter, right? Okay. And so let's write it down. What are the given values? Area of the channel A, since it's a rectangular area, it will be 0.75 times what? 0.5 meter square. Okay, you'll find that one. The next one is if the velocity is 2 meters per second. Now here we need to work a little bit. This velocity, it's coming from this channel parallel to this channel right here. So what I will write down here, the velocity parallel to the channel is 2 meters per second. And I don't know anything else, so I can write down what we need to find. To find the volumetric discharge Q, which is A times V, right? That's what we need to find out. We'll do that. If you are done, I will move to the next slide. Done, everyone? That V is parallel to the channel, but what was the condition of that V? Like this one, that V needs to perpendicular to the area. If you look at here, it's not perpendicular to the area, so we need to do something. What we can do? We need to take the components, right? Okay, that's what we will do here. Yes. So I will just try to draw this is 20 degree and that is V, and this is the area. So I need to find out the velocity which is perpendicular to that area, right? What is the angle here? Again, it's 20, and I will name that V, maybe the horizontal component, okay? So V horizontal is V perpendicular to the area, and that will be V cosine 20 degree. What is that? What is the value of that? Say it loudly. 0.8. Okay. So that is 1.88 meter per second, right? Okay. That was the pipe and that was the velocity. Now we can calculate what was the area? Yeah, did you find out the answer for that? Or I will just write down this one. So for this one, that was meter square, meter per second. So the final one will be meter cube per second. But what will be the answer? .7. Okay. So 0.7 is the answer for the volumetric flow rate. That means 0.7 meter cube per amount of water is flowing through this pipe or this channel per unit second. That is huge amount of water. Okay, so that was easy. The only thing we needed to find out or make sure that the velocity has to be perpendicular to the area, right? Okay. So complete that and then we can start working on part B, which is from your textbook exercise problem number 54. So let's start working on that. Can anyone read the question? Question number. Okay. Thank you very much. So we have a tank here and we will consider this tank as our control volume. Okay. That is the, I shouldn't use the arrow sign. You will be confused. Okay. So this one is the control volume, like this dotted line is the control volume here. Now, for this control volume, how many inlets we have? Number of inlets to A and B, right? And how many outlets we have? Okay, so we have one outlet. One, which is C, right? So the question is saying through A and B, some carbon dioxide and nitrogen flows through A and B within that control volume, they get mixed up, and through C, a mixture of those are coming out. So let's write it down, what are the given values, and then we will know what is the unknown we need to find, okay? So what is the very first thing you know? VA, right? Which is the carbon dioxide, 10 meter per meter per second. What is the next one? VB, which is nitrogen, 6 meter per second. What is the next thing you know? Okay, so pressure A and B, right? Is 300 kilopascal. Now, they didn't say anything, it's absolute or gauge. Since they didn't mention anything, we will consider that as gauge pressure, okay? Because if it was absolute, they would mention that this was the absolute pressure. So I will make a note here that this is the gauge pressure, okay? What else we know? Temperature 250 degrees centigrade. Now from the unit, it's not Rankine, it's not Kelvin. So the pressure is at the temperature is relative or the absolute. Yes, good. Okay, so I'll make that one also. Now the last thing is they give you the mixture of density. That means the density of C, density of mixture (1.546 kg per meter cube), right? All of these are the given values. Now, after hundreds of given values, what we need to find? What we need to find from these? The velocity at C or the velocity of mixtures, right? So V, C, V, mixture. What is that? I need to find out that. So we are done with first step, that we identified the given values. We identified what we need to find. Now the next step is we need to connect, or we need to find one equation which can connect unknown and known, right? Now from the given values, we have rho, we have density, we have velocity. We kind of know that we need to use the mass conservation equation, right? And they said that the steady rate at C. So obviously we need to use the steady mass conservation equation. Also, I said we will not use anything unsteady. So we don't need to start from the very beginning. Rather, we will start from the steady mass conservation equation, okay? So let's start mass conservation equation for steady flow. If I can remember properly, that should be inflow rho AV, outflow rho AV, right? And you told me how many inlets we have here? We have 2 inlets and 1 outlet, okay? So that means, and A and B, those are the inflow or inlets. So what I will write down, rho AV A plus rho AV B. And we have only 1 outlet, rho AV C, right? Now, I think you are in better position than me because all of my given values in the previous slide. So what you can do, identify which values are given and write down in that way, okay? So do you know rho A at this point? You don't know rho A, and you can't use that one also because we have a pressure and temperature. We need to calculate that. So we will work on that. Rather, at first write down what things we already know, okay? So I will just write down rho as it is. Can you calculate the area of the A? Is there any way you can calculate? Pi. Yeah, pi d square over 4 or pi r square, right? And what is the VA? 10. Okay. I don't know anything about rho B also. I will just, and for area here, pi 0.15 over 2. Okay, I should use different type of parentheses here. Okay, I will just change a little bit. What is the velocity for VB? 6. Do we know the density for C? 1.546. We know the diameter here, so pi 0.1 square, and we don't know the velocity there, right? Okay. Are we good up to this point, everyone? Now we need to do 2 more things. We need to calculate rho A and rho B. How to calculate rho A and rho B? You know the temperature, you know the pressure. Ideal gas law, great. We know that there is an equation called ideal gas law. We need to use that. So if for any reason they gave you the rho A and rho B, your life would be so much better, but they didn't give you. So we need to calculate that. So let's calculate rho A and rho B for the temperature and pressure given, okay? So I'm moving to the next slide. Rho A, what was the equation for the ideal gas law? P equals to rho RT. So rho equals to P over RT. A is the carbon dioxide. So, and the P is what? 300 kilopascal. And we need to add the atmospheric pressure as well, right? And the atmospheric pressure is what? 101.3 10 to the power. I will just make a note. P atmospheric. Can you give me the R value for the carbon dioxide from the appendix A? And the temperature will be what? 250 plus 273 K. Give me the R value for carbon dioxide. $188.9. Okay, and you got that from appendix A, right? So I will just appendix A, and this whole thing is absolute temperature now, right? Okay. So do the calculation here. What will be the rho with proper unit? While some of you are calculating this one of you can help me with the next part so we can save some time. The pressure was same again. Find out the R value for nitrogen. 296.8. Okay. And everything else will be same, right? $250 plus 273. This time I'm not writing any notes because everything is same. Give me the value for row A and row B with proper unit. Say it again, 4 point. For carbon dioxide, I got a little bit different. That's what I got, 4.06. So I will write down that one. Check your calculation. Okay. 4.62 kilogram per meter cube. What about this one? Rho B or rho nitrogen? Yeah, that's what I got. 2.585. Okay, now we have everything. The only unknown is mixture velocity and a big equation we need to solve. But other than that, rest of the part is easy, right? So what you can do, you can use these two values on this equation here and find out the value for VC. So what I will do, I will move to the next slide if you are done with this one. And I will try to add all the values on that equation, okay? We were enjoying working on that so much that we didn't keep track of our time. I will start from this point on Wednesday, okay? Make sure you bring your class example 15. We will start from this point. Thank you very much. Okay, so the plan for today, we will complete the class example 12, which is class example 15 on your part. That should be class example 12, okay? So we should complete that one. And then we will go through very quickly on some other class examples, but those are already worked out. You should have a package where I gave you 3 class examples, like class example 4.2, 4.3, and another example from the exercise. So we will go through very quickly on those. And after that, we'll be done with the mass conservation. And then we will start the second conservation principle, which is the energy conservation, okay? And on that, we will go through the Euler's equation of motion and a little bit of Bernoulli's equation. And I think up to that point, I can cover today, okay? That's what we will do. Now you have one homework due, which is Monday. I extended the time till midnight. So you will be able to ask me question on Monday also, if you have any question. And there will be a quiz. Most probably that is quiz 6. I can't remember what will be the number. That is again the reading quiz. That will be for next week. Open book, anything. You will just go through the textbook and answer all the questions. Okay. So that is the plan for today. And okay, let's start working on that. We developed the equation for mass conservation for steady flow because we are not doing anything with unsteady flow, right? So for steady flow, we finally came up with the expression which said that incoming flow should be equal to the outgoing flow in terms of volume, in terms of mass per unit rate of time, right? Per unit time. It can be per unit second, it can be per unit hour, anything. So for class example 12, the question was, through inlet A, carbon dioxide is entering into the tank. Through B, nitrogen is entering into the tank. They are mixing up within the tank, and as a mixture, they're coming out through the outlet C, right? So we had two inlets, one outlet, and we listed all the given values, and we found out what we need to find out, which is BC. And then we started working on that. We wrote the equation, and we saw that we know the AV for A, AV for B, and rho A for C, but we don't know rho A, rho B, like the density of carbon dioxide and density of nitrogen at that pressure and temperature. So obviously, whenever you have a gas within a certain temperature and pressure, you instantly know that you need to use the ideal gas law to calculate the density, right? So that's what we did. For your class, we already did the density of carbon dioxide and density of nitrogen. Now we will start our class from here. Like we will use this value here, okay? And then we will calculate the value for VC, okay? So let's do that. For this part, so what was the density for A? Carbon dioxide, 4.062, okay. And the area of that one was pi 0.1 square 10, okay. Pi 0.1 square 10. And that was the A, plus the density of B is 2.585. Pi 0.15 over 2. Pi 0.15 over 2, 6, right? Equals to 1.456. 1.45. Is that the correct number? 456? Step that. 546. 546 pi 0.1 square VC. Okay. Now you need to calculate the VC. Okay. So do that. Give me the value for this whole thing, and this one, and calculate the VC. Do that. I'll be here. If you have any question, just ask me. Okay. Yes. So that is the R. The radius was 5 than that. Check the calculator. It's close, but it's not correct.
31.9.
Ah, that's what I got.
So if you do the calculation properly, you should get 31.9. Okay, so give me the number for this one. 4.06, 5.1 square, 10. What is the number for that one? 1.27 or something like that? 624. Okay, plus. Say it again. 274. Are you sure this one is 1.624? That's what I think. That should be here, 1.27. I don't have the breakdown of calculation, but from section 1, I kind of know that it should be 1.27. Okay, 0.274. And what is the answer here? No, here, just 49. Okay, so the VC is 1.27 plus 0.274, 0.049. If you do the calculation properly, you should get something around this number, maybe a little bit less or more than that. And since it's a velocity in SI system, what will be the unit? Meters per second, yes. Okay. So that was the answer for class example 12B. Now for mass conservation, you will not see that much variation in the problem. Most of the time, like anytime, either it will be gas or liquid. Obviously, those are the fluids. And for liquids and gas, anytime you can start from working this equation like inflow to outflow, because we are not doing anything unsteady in this course. So everything should be steady. So this is the equation for mass conservation all the time. Now, if you have the liquid, you can cancel rho inflow equals to rho outflow, but I recommend always start from this point so that you will not get confused. And after that, you can cancel the rho, okay? Now, I gave you few other class examples just to do more practice here. There is no trick, no surprise, nothing. Just to do more practice, I have given you that. So class example 4.2 and 4.3, that is from your textbook. If you have that, if you prefer the color version, you can look at your textbook. You will get the colored version, but your copy is the black and white one. So here, the example 4.2 is for liquid, okay? And this is a fire extinguisher. You have two outlets, the same diameter and everything. If I say that one is outlet 1 or outlet A or B, something like that. This one is outlet 2. Most probably it's in your copy, it's A, B or something like that. So these are the outlets, and this fire hydrant is getting water from some source from the ground. So that is the inlet. So you have actually one inlet, rho AV inlet, but you have two outlets. So you need the summation of rho AV outlets, right? And you will find out the individual value, either it's given or you need to find out. Now, the thing is, since the fluid here is water, so water at density of water at inlet should be equal to the density of water at outlet, right? So you can say here, only for this case. So after that, you can work on that. Okay. So that is the class example 4.2. Now for 4.3, what is the fluid type, gas or liquid? 4.3, it's the gas, it's the airflow. So some air is entering through this way, that is the inlet, and that is going out through that way, so that is the outlet. And inside that, the heat energy is applied here, like the heat obviously will change the density of the air because that will increase the temperature. Now you have one inlet, one outlet. So you can write down PAV in, PAV out. You don't need the summation sign, but if you want, you can use that. Now, this time, since it's the air with the temperature, you can't say this one. So you need to use the density, and if the pressure and temperature is given, you need to find out that. You need to make sure that the pressure and temperature should be absolute pressure and temperature, and using ideal gas law, you can find the density if it's not given. Okay, so that is example 4.3. There is no tricks, nothing, straightforward. But the last one, there is a small trick for this one. Here, this pipe or this channel, this is the triangular channel. You can see that. Now, what is the total height of this channel? 0.5 meter. But you can see the water is not up to 0.5 meter. There is an empty space, right? So water is up to 0.4 meter. So when you calculate the area, like Q equals to AV, that A should be just the area of water, okay? Here. So you need to know what is the width here. I think I gave that width in your copy. So that should be the one. 0.43 or something like that. Oh, okay, 0.32. Yeah, I found that using the similar triangle, so you can do that. So the area will be what for this one? Half times base times height should be what? 0.4 or 0.5? 0.4, yes. So that is the only trick here, that you need to calculate the proper area. Other than that, everything is same as what we did for class example 12A. Okay. So other than that, I don't think you will see any other variation of mass conservation principle. It should be within these types of problems. Okay. Now you are fully ready for your homework 7. You will see there is one example about like gas, one example about not example, like one question about gas, one question about the liquid or something. So start working on that. And if you have any question, just stop by or email me, or you can ask me on Monday. Okay. Are we good? Mass conservation. For mass conservation, you will not see that much tricky question or something. It is always pretty straightforward, always mass in equals to mass out. So you should be fine. Okay. Okay. So if you don't have any question about this part, we can start our second part, which is the energy conservation. Okay. So you should have a class lecture copy for lesson 24 or 5, or what is that? Yeah. So we will use the same lecture copy for today and for Monday. So please make sure you're bringing that on Monday also. Okay. So I'm stopping sharing this one. And I will use the other one, which is the Bernoulli's equation here. Okay. So the Zoom people, can you see that screen on your computer? Okay. Here. So these are the learning objectives for today and for next class. We already did the complete class example 12. Now we will start working on the energy conservation. Now, though we said that we will start the energy conservation, we need to know some background of or some basis for the energy conservation. So we will discuss the Euler's equation of motion, and then we will discuss the Bernoulli's equation. I know some of you have heard about the Bernoulli's equation, right? You don't have to remember the principle, but just tell me that you heard the name. Okay, that should be enough. We will review the principle, so no problem. Okay, so the Bernoulli's equation, like Bernoulli's around mid-18th century, he stated that for a fluid particle, the total energy should be summation of some other energies. Okay, we will discuss that. So once he stated that, after few years after that, Euler's, he actually came up with the mathematical expression for the energy equation. So in our class, we will at first discuss the mathematical expression, and then we will discuss the actual equation, okay? So to do that, you know this is a fluid particle, and you know a little bit about the streamline. The streamline is a line